Okay, we're doing question 3, chapter 5, managing bottlenecks in manufacturing processes. Canine Kennels Company, CKC, manufactures two types of dog chew toys, A and B, sold in 1,000 count boxes that are manufactured and assembled on three different workstations, W, X, and Y, using a small batch process. See the figure below. We'll get to this figure in just a moment. Batch setup times are negligible. The flowchart denotes the path each product flows through the manufacturing process, and each product's price, demand per week, and process time per unit are indicated as well. Purchase part and raw materials consumed during the production are represented by inverted triangles. CKC can make and sell up to the limit of its demand per week. No penalties are incurred for not being able to meet all of the demand. Each workstation is staffed by a worker who is dedicated to work on that workstation alone and is paid $6 per hour. The total labor costs per week are fixed. Variable overhead costs are $3,500 a week. The plant operates one 8-hour shift per day or 40 hours per week. So that's the information we have. Let's go through the process flow. Okay, the flow chart for product A is that it starts with a $2 raw material input, goes to step 1, which is station W, and that takes 11 minutes to complete. Then it goes to step 2, which is station X, which takes 10 minutes. After that, a $3 part is added. Then it goes to step 3, which is the last step, and it's station Y, and this step takes 13 minutes to complete. Some information they've given on product A. The price is $55 per unit and the demand is 95 units per week. Now the flowchart for product B, a $6 material is inputted into step 1, and the first step is station X, which is 14 minutes. Now if we look at product A, first step was station W, whereas in product B, the first step is station X. So you just have to be really careful when reading the question so that you can answer the problem correctly. So after step 1, it goes to step 2, which is station W. It takes 19 minutes. And after that, a $5 purchase part is added. Then it goes to step 3, which is station Y, and that station takes 10 minutes to complete. Some information about product B. Selling price is $65 per unit and its demand is 90 units per week. Okay, so the question is, which of the three workstations, W, X, or Y, has the highest aggregate workload and thus serves as a bottleneck for CKC? Okay, so before solving any question, it's always a good advice that you copy all of the information down in Excel so that it's easy and quick to do your calculations. So what I've done over here is I've just copied this information into Excel. The load data in minutes, workstation W, X, and Y, and the time it takes in minutes to complete each step. Step W for toy A takes 11, workstation X takes 10 minutes, and workstation Y takes 13 minutes. You can see from over here, the first step, W, took 11 minutes, and X 10, and Y 13 minutes. So I've copied that over here. And for toy B, the first step is station X is 14 minutes, so under X, I put 14 over here. Step 2 is W is 19 minutes, I put in 19 over here. And step 3 is 10 minutes, I put in 10 minutes over here. The next thing I copy down is the raw material and the purchase part for each of the toys, toy A and toy B. So for the raw material, for product A, there's a $2 raw material and a $3 purchase price. So I put in $2 over here and $3 over here under toy A. And For toy B, it's $6 and $5. $6 and $5. The next thing I put in is the price, the selling price, and the demand per week. So the selling price for product A was $55 per unit and 95 units per week. So I put in $55 and 95, while for B it's $65 and 90 units per week. So it's 65 and 90 units per week. The next thing I put in is the total labor per workstation. That's one person per workstation. Other information we had was variable overhead cost per week was $3,500, which we got it from our question. Over here, the variable overhead costs are $3,500 per week. Wages per hour, $6, hours per day, $8, and days per week, 5. Now, to solve this problem, we need to find the total load time of each of the workstations. So the first thing we need to do is find the formula, and the formula is to find out the total load time is the time for product A multiplied by the demand for product A plus the time for product B multiplied by the demand for product B. So let's just write this information down. Workstation W, X, and Y. Total load product A and total load for product B. And this would be the total for one workstation. Okay, how do we calculate the total load for product A? We take the total time of workstation W and multiply by the demand of product A. So that would be, put in an equal sign, the time for toy A, product A, and for W is 11 minutes, and then we multiply that by the demand, which is 95 units per week, and we get 1045. We do the same for workstation W. 10 multiply by the demand, we get 950, and same thing for Y. 13 minutes multiply by demand, which is 95, so that's 1235 minutes. And we do the same thing for product B, workstation W. 19 minutes multiply, now the demand for product B is 90 minutes, so we get 1710. For X, that would be 14 minutes multiplied by 90 units, 1260. And for Y, 10 multiplied by 90 gives us 900. Now we just need to add total load of product A and product B. So this would be simply this plus this, and we copy it down. So you can see that we get the answers over here, and the workstation with the highest number of minutes is workstation W, because it takes 2,755 minutes at workstation W, whereas in workstation X is 2210 and at Y is 2135. So our answer would be, which of the three workstations has the highest aggregate workload? So that would be workstation W, and this serves as a bottleneck for CKC. And if you want to know the number of minutes as well, so it would be workstation W, and the total minutes is 2,755. That's the end of question 3.